Okay, so here is part 2 of our arithmetic sequences notes video. Not quite sure where exactly I got cut off, but we had just looked at this example. We said yes, it does have a common difference of 3, and now I just want to discuss how the recursive formula works. Now, it's pretty intuitive how to find the next term in the sequence after 26, if every time our common difference is 3. So really what I'm going over in this is the notation. So if we have f of 10, the way we're going to find the 10th term is we're going to be using, sorry about that. We're going to be using the previous term, which is what we're talking about when we say f of n minus 1, and the term before the 10th term would be the 9th term. So if I take the 9th term and I add my common difference of 3, so that's what we mean by D, then I will get the 10th term. Now, if I look back up at the sequence up here, the 9th term is right here, 26. So to kind of reiterate what I'm doing, I'm going to take the number 26, add the number 3, and that will give me my 10th term, which is 29. So we know f of 10, which is the 10th term, is 29. Now, to find the 11th term, I take the previous term, previous to 11 would be 10. I'm going to add my common difference, which is 3, and, knowing that the 10th term is actually 29, I'm going to take 29, add 3, and I will get to 32, which is my 11th term. F of 11 is 32. Now, there's a point when this can kind of get a little bit tedious, having to add on each time, but I'm going to have you practice it again on your own right here. So I want you to write the recursive rule for each arithmetic sequence. So if we are finding f of 5 and f of 6, how are you going to format the recursive rule for those? So we got f of 5, f of 6. So knowing that the recursive formula is always f of n minus 1, or the previous term, plus d, how are you going to write out these in the proper notation? I would like you to complete this example on your own. Make sure you pause the video. Okay, so if we are looking from term to term here, to get from 18 to 23, we had a common difference of 5, 23 to 28, common difference of 5, and 28 to 23, also 5. So we can say that D is 5 here. Now, to find the 5th term, okay, we have 1, 2, 3, 4 terms so far. To find the 5th term, I'm going to take the previous term, which is f of 4. Oopsie, I don't know why I just wrote D there. And we're going to add on our common difference, which is 5. So f of 4 plus 5. Now, we know that f of 4, the 4th term, is 33. So 33 plus 5 will get me to 38. So f of 5 is 38. Now, following in the same way, f of 6, we would take f of 5, add 5, and get our 6th term. Now, our 5th term was 38, plus another 5 is going to give us 43. So our 6th term is 43. So what about if we want, for instance, the 101st term, f of 101? Seems like a lot of work to have to use every previous term over and over again to get all the way to 100. So, the recursive formula is good when you're just trying to find the next one, and, it's really easy to just add on a common difference. To find a term, a little bit more out there, like the 101st term, we want to use what we call the explicit rule or explicit formula. So while the recursive formula is always based on the previous term, an explicit rule is a rule for a sequence that gives a of n. So again, that's just the nth term, or a sub n, as a function of the term's position number n in the sequence. So now, instead of always going off of the last term in the sequence, we want to just be able to use the position. So if I wanted to find f of 101, I want to just use that position 101 and be able to jump right out there into that part of the sequence. So the way we use the explicit formula is you do need the first term, and you need to know what the difference is. So we at least need to know what number we're starting with, and we need to know what number we're adding on each time. And then we can build this explicit formula. Now we want to think of, now that I'm throwing in this a of n, or this is like the nth term, a sub 1 is the first term. And these are, interchangeable notations here. F of n, a sub n, f of 1, a sub 1. We're referring to the first term in both these places. We're referring to a nth term in both of these places. Okay, so explicit formula. I could find any position that I want. So that's what we mean by this n. It could be 101. It could be 2. Any position I want. If I take the first term plus n minus 1 times my common difference. I'm going to show you on the next slide why it works out this way. So let's see right there. Okay, so if I have a sequence like 2, 5, 8, 11, 14, what's happening each time is I'm adding 3. Well, we've had this example a lot about 3, but if you just look at the terms and how we get to them, in a recursive way, we have the first term, which is 2. To get to the second term, we take 2 plus our 3. To get to the third term, we take our original 2 and we add another additional 3, which is a total of 6. To get to our fourth term, we add yet again another 3, and we'll get to our next term. And what you should notice here is that the number of 3s we end up adding is actually just one less than the term that we're looking for. So you could look right here. If I'm looking for the second term, I only added 1 3 there. When I'm looking for the third term, I end up adding that 3 twice. See, there's no addition in the first one. It comes afterwards. If I'm looking for the fourth term, I ended up adding that 3 different times. Fifth term, it happened 4 times. And so the nth term, if it's always 1 less, I know that it's going to be to the n minus 1. I'm always going to add that many common differences to my first term. And this is how we're going to use the formula to really jump anywhere we want into the sequence. So if I want to find f of 24, okay, so here's, and then our 1 f of 101. So here's how we do it. We take the very first term. Okay, so my very first term is f of 1, and I'm just going to kind of write this out, I guess, a little more generally. So I have f of 1. I'm going to add my n minus 1 is going to be 24 minus 1, because I'm looking for the 24th term here. And I'm going to multiply that by my common difference d, which is this 3 that I keep adding on each time. Now, f of 1 was actually 2 right here. So I'm going to take 2 plus, and I'm just going to simplify this right here. 24 minus 1 is going to be 23. So I want 2 plus 23 times 3. Then I'm going to work that out. Well, 23 times 3 ends up being 69. 2 plus 69 is going to get me 271. So I already know that the 24th term, if I did this over and over until I got to the 24th term, I would get this number 71. And now I do not have to do this repetitive addition. Okay, so for the 101st term, I still, doesn't matter where I'm trying to get that term in the middle, I always start with the first term. The first term is 2. Now my n minus 1 is not going to be, 24 minus 1 anymore. It's going to be 101 minus 1, and then times 3. Now I can simplify my 101 minus 1, which is 100. So I have 2 plus 100 times 3, and that's going to be 2 plus 300, or 302. Okay, so there's sometimes a little bit of rearranging what we might want to do with this explicit formula, just to kind of collect our like terms and, do that kind of simplifying that we did when we were solving equations. So this is the same sequence. Like I said, no need to write it again. We have our explicit form, which is 2 plus n minus 1 times 3. Now, this is where I could plug in any n. It could be 24, it could be 101. It's all ready to go with me, plugging in that n right here. Now, there is some simplifying that can happen. We can get rid of our grouping symbols by distributing our 3, which is what happens right here, and we say f of n equals 2 plus 3n minus 3. We also can combine our like terms here with our 2 and our negative 3. And so all the way simplified, our explicit form becomes into this equation, this function notation, f of n equals 3n minus 1. And this should look similar to some things that we've been graphing in class, graphing in ALEX. We might have different variables here, but it's still that variable with no exponent. We just see one of them. We should be thinking about linear equations here. And this is really why we start with arithmetic sequences before we get into linear equations, because it really builds into that. Okay, so I'm gonna go over this page. This is kind of our summary page. We are going to go over some more examples in class, but this is all I wanted you to take notes on at home. So just to wrap it up, the explicit rule of a sequence gives a sub n as a function of the term's position. So we want to know, like, what position are we looking for? Are we looking for the 101st, the 50th, the 24th? What is it? So it's always going to be based on that input of the term that we're looking for, and we actually literally use that and plug it into the formula when we do our n minus 1. Another way to define a sequence or to find new terms in the sequence is with the recursive rule. The recursive rule is always based off of the term before, and that's where we see that we can find f of n if we have the previous term, f of n minus 1 plus d. Now really there's no plugging in happening here other than, in a notation, but I'm not going to say like, oh, if I'm looking for the 24th term, I'm going to plug in the number 24 and actually operate with that. No, all we're referring to here is the term before. So in order to use the recursive formula, we have to keep knowing the term before and using it and using it and using it. Back to the explicit formula, we can actually use that number term that we want and plug it in as an input. So those are the big differences between the two rules. We will be discussing them more in class, and if you had any parts you were confused on, maybe put a star, put a little question mark, and talk to me about that section of the video in class. All right, see ya.